Hello, good day everyone. In this video, I'm going to present to you about some principles and application of laser plasma accelerators. In this presentation, I'm going to explain some of the physical processes involved in laser plasma accelerators to highlight the uniqueness of the resulting particle and radiation beams and to emphasize their relevance for fundamental and society applications. So this is the outline of this presentation. First, we have electron beams, followed by proton beams, X-rays, and the last is the application. Um, for electron beams, as we have seen in this figure, the diagram of laser plasma accelerator. For figure A, this is the schematic of the LUX laser and electron beam line. For figure B, this is the structured plasma source supplied with H2 and doped with 10% N2 in the front for the controlled injection of electron bunches into the laser-driven plasma wave. Here, the longitudinal accelerating electric field is generated by the panderomotive force of an ultra-short and ultra-intense laser. So this force pushes the plasma electrons out of the laser beam path, separating them from the ions. And then this creates a traveling longitudinal electric field in the wake of the laser beam with a phase velocity close to the speed of light, most suitable for accelerating particles to relativistic energies. And also, this electric field can reach amplitudes of several hundred gigavolts per meter. Here, electrons need to be injected into the wake field with a sufficient initial energy so that they can be trapped and accelerated. Experimentally, we have two injection mechanisms have recently demonstrated the generation of high-quality monoenergetic electron beams. In the first mechanism, so here in figure A, um, a single laser pulse is used to drive the wake field to large enough amplitude such that electrons are injected into the rear of the first wake oscillation through the transverse, breaking the plasma wave. The electrons surf the wave, and after outrunning the wave, they form a monoenergetic electron bunch. So this is referred to as the what we call the bubble region. So far, laser parameters used in published experimental results have been unable to directly access this region. Instead, the conditions for transverse wave breaking are eventually met as result of laser pulse evolution as it propagates in the plasma. With current laser technology, electron beams in 100 millielectron volt range have been produced over millimeter distance. So according to the reference 2 to 4. So the relative energy spreads of the order of 5 to 10%, and a charge of hundreds of picocoulombs. So here, for the figure B, a 1 gigavolt, giga electron volt electron beam has been reported in a recent experiment where the laser pulse was guided and evolved over a few centimeters in a capillary plasma discharge. The second mechanism or this figure B is based on the use of several laser pulses with the same wavelength and polarization. So the first laser pulse, the pump pulse, creates a wake field, whereas the second laser, the injection pulse is only used for injecting electrons into this wake field. The laser pulses collide in the plasma and their interface creates an electromagnetic beat wave pattern that pre-accelerates some of electrons. Okay, so here in this figure we have the next of electron beams, which is the proton beams. So here, in contrast to electrons, ions are best accelerated by a low frequency or even a quasi-static electric field compared with the electron plasma wave frequency. So the rapid field oscillations associated with an electron plasma wave average up to zero net acceleration for an ion. In the conducted experiments, the mechanism of ion acceleration can be um, classified into two categories. So on the basis of how the electric charges separation that produces the quasi-static field is generated. So that is the panderomotive and the thermal explosion acceleration. So here in panderomotive acceleration scenario, the charge separation is generated by the panderomotive force of the laser, which sets up a charge imbalance that accelerates ions into o intons. So it is indeed a low frequency force with the laser pulse during the duration as characteristic time. This mechanism includes forward ion acceleration at the surface of an irradiated solid target and transverse ion acceleration associated with the self-guided laser propagation inside a low density plasma. So this is based on the reference 7. And in the thermal expansion type scenarios, the charge imbalance is maintained by heating a fraction of the plasma electrons to a very high temperature. Then the resulting electron thermal pressure drives an expansion of these hot electrons around the target, setting up a large amplitude electrostatic field at the target vacuum interface. In these cases, ions will be accelerated out of the target periodically to its edges. To these thermal explosions can be associated the accelerated ions detected behind peak targets and the high energy plasma plume emitted from the laser irradiated surface. The relative importance of this various acceleration mechanism has been largely debated over the past decades with conflicting numerical and experimental evidence. Recent studies, however, show that both mechanisms can coexist and that one can dominate over the other depending quite subtly on the interaction parameters. Here, several paths for beam optimization are now being actively pursued. The first is to operate with the ultra-thin targets in the sub 100 nanometer range, which requires ultra-high contrast laser pulses. Improved acceleration with such targets has been reported recently. Another way to control the energy distribution is to engineer the target back surface to the selectively accelerate ions in given charge state or to a given energy. An alternative path for energy selection relies on the laser-triggered micro-focusing devices, the relevance of which for beam steering has been demonstrated experimentally. Most experiments studying ion acceleration by high-intensity lasers report the detection of a large number of accelerated protons, even when using metallic targets. These protons can be tracked back to hydrogenated contaminants deposited at the target surface. In the first experiments, the proton energy distribution was Maxwellian-like with a sharp cutoff at high energy. So for example, proton beams with energies up to 58 mega electron volts have been measured at the Lawrence Livermore National Laboratory with the now dismantled Nova Petawatt laser. In some experiment, the target was heated before the interaction to evaporate the hydrogenated layer. This enabled the detection of energetic ions with higher atomic numbers. Proton beams produced by rare surface acceleration show good collimation, increasing at higher proton energy and very low transverse emittance. Now, we will move for the X-rays. So here, despite of 100 years of history, the production and applications of X-ray radiation remain extremely active in multidisciplinary fields. Spectacular increase in brightness and decrease in pulse duration of X-ray beams are now foreseen owing to the progress made in laser plasma interactions. So as we can see here in this figure, the principle of betatron radiation produced in a weak field cavity. The electron is accelerated to relativistic energies and wiggled in the cavity. As a result of this motion, an X-ray beam is emitted in the direction of the electron momentum. At the frontier between plasmas and accelerators, ultrashot X-ray sources are produced using electrons accelerated in laser and electron beam wake fields. So based on radiation from moving charges, the most compact and promising schemes rely on the wiggling relativistic electrons produced in laser plasma accelerators, either within plasma itself in a counter-propagating laser beam or in a permanent magnet undulator. These sources, capable of combining femtosecond durations together with collimation, offer a remarkable perspectives for countless applications. So for the application, um, for some application of this topic, I chose the medicine. So up to now, X-rays with energies of few mega electron volts represent the vast majority of ionizing radiations used for cancer radiotherapy of several million patients throughout the world. X-rays are commonly used because they are produced using flexible, compact, and affordable machines. Higher quality, more than energetic electron beams, such as those produced by laser plasma accelerators, could be used for radiotherapy and provide better clinical results. So it was shown that such beams are well suited for delivering a high dose peak on the propagation axis. A sharp and narrow transverse penumbra combined with a deep penetration. With more than 3,000 patients worldwide with successful clinical results, proton and hadron therapies are still emerging, but representing promising methods for the specific treatment of deep tumors and radio-resistant cancers. The infrastructure's requirements, which include accelerator, beamlines, massive gantries of more than 100 tons of building, are not accessible to the majority of radiotherapy centers. With the outstanding progress in laser physics and fast development of the high-power laser systems, several laser-based projects have emerged with the goal of reducing the cost of proton therapy treatment. This cost could be cut not only by changing the accelerator itself, but mainly because the building footprint would be strongly reduced and the gantry could be replaced by a smaller and lighter structure. Several severe conditions have to be met before considering such an approach for medical applications. So here it is necessary to increase the proton energy up to 200 milli electron volts, for which petawatt class lasers will probably be required. Second, have enough protons at this energy to treat patients in sessions of a few minutes, for which high repetition rates could be needed. So about 10 cycle per second. And the third is have a reliable and stable laser plasma accelerator. The dose requirement and dose profile could be achieved with particle selectors or structured targets. This promising application is also extremely challenging as it requires the development of high contrast petawatt lasers operating at 10 Hz, as well as dedicated research activities in target such design and intensity interaction. In related field, lower energy protons of several mega electron volts delivered with compact cyclotron machines of a few are used to produce radioisotopes for medical diagnostics. A laser-based alternative has been considered but does not seem economically competitive because higher repetition rate lasers could be required with a cost in excess of existing accelerators. So here are the references of this presentation. And that's all for this presentation, and thanks for watching.